So welcome to this second video on biasing field effect transistors. So here we will see how to bias specifically JFET, that is junction field effect transistor, and the depletion MOSFET bias. Okay, because see the JFET and DMOSFET biasing conditions are same or similar. Okay, so we will look them simultaneously. The enhancement MOSFET biasing conditions are different. You know the basic difference, that is in case of JFET and DMOSFET the gate control voltage that should be negative, while in case of eMOSFET the gate control voltage that should be positive, and that's why the biasing network that differs. Okay, so we will look at JFET and DMOSFET biasing simultaneously. Mainly first we will focus on the fixed bias configuration, and then we will also analyze the other networks, other configurations. To this output loop, let us apply KVL to this output loop. That is going to be, you can say here, that is VDD minus ID into RD and minus VDS, that is equal to, right? So that is VDD minus IDRD minus VDS is equal to 0. That gives VDS is equal to VDD minus IDRD. So thus we have been able to find out VGSQ, IDQ as well as VDSQ. So these three quantities we have found. We have found the operating point VGSQ and IDQ. Corresponding to that, we have also found the output voltage. Fine. Okay, so let us try to understand this thing in terms of that is graphs. That is, this is one more way, graphical way is one more way to find out the operating point. So let us try to find out that. Fine. So that is, we know that is transfer characteristic for JFET and DFET, DMOSFET, that is VP, and this is VGS has to be negative, and this is just following this equation, that is ID is equal to IDSS 1 minus VGS over VP square. You get this characteristic. Fine. On this IDQ I have got from the previous network, so that is VGG minus VGG and IDQ I have obtained. The Q point is obtained now because VGG is already obtained. VGS is equal to VG minus VGG, and IDQ corresponding ID is obtained from the previous equation, that is from this equation. Okay, so VGS is known, VD is known, so now we can find out the operating point, the combination of these two, that is minus VGG and IDQ, that will give us the operating point Q. Okay, we have also found the interesting point, that is VDS corresponding to the Q point, so that gives us VDSQ. Right, so this is going to be the method or for all the type of biasing network. We may not discuss every time the graphical method or graph. We may not show the Q point on the graph. Here we try to show the Q point on the graph. The thing is, it is on the transfer characteristic. Okay, and not similar to the BJT. In case of BJT, it is going to be on the output characteristic curve. Here it is not on the output drain characteristic, but it is on the transfer characteristic. Fine. Okay, now let us look at the AC analysis of the same circuit. Okay, so I've shown here the same network again. Now say what is the job of C1 and C2? We know that is C1 and C2 both are capacitor which blocks DC. So for the previous DC biasing network, they were not this circuit, that is before this part and after this part, they were not there, this part and this part, they were not there in the DC biasing. But now for AC biasing, C1 and C2 both of them are shorted. C1 and C2 are shorted, and now we remove the DC source. So that is, DC source is like this. Okay, so in this case, if we see AC source, that is VG. Now we find out the gate voltage. Actually I would have shown this is a small v into G, fine, and capital G, that is DC plus AC, right? So small v into G, that is going to be minus VGG plus V in. You can see V in capacitor is short for it. This is shorted, and that is directly available across RG. This is shorted, so V in, that is directly available across the RG. So that means the gate point terminal that is having actually, when we consider superimposition of both DC source and AC source, that is actual VG, that is going to be minus VGG plus VE. Okay, and if you see VGS, we are interested in VGS. Okay, what happens to the operating point, or what happens to the around operating, how the variations in the input will be there. So VGS is equal to VG minus VS, and VS is 0, but VG is equal to minus VGG plus V, so V in minus VGG. So that's how this is going to be, okay, rated. So now let us actually try to find out how the amplification process happens. Yeah. So here you can see, yeah, this was the VGG point. That is Q point is this corresponding, that is VGG, and this is our IDQ. Okay. Now VGG, that is suppose input V in is there. So because of input V in, let's say it is AC, and these are the variations in the AC. Actually the waveform is not proper, but I want to show that they are of same amplitude, and that's why the amplitude on this side correspond, because this is a line, right? So they are, this gap and this gaps, positive half cycle, and this gap are same. But when you translate them on the ID curve, that is corresponding to this, you can find the ID, that is this, and corresponding to this lower half cycle peak, that is negative half cycle peak. This is the corresponding ID, and you can see the, or because this is quadratic, okay, so there is more amplification on the positive half cycle and less amplification in the negative half cycle. This is more than the peak at the negative half, but they are in phase. Okay, that means say ID that is in phase with VE, whatever the direction of VE, ID is in the same phase. Okay, similar to the transistor, that is IB, IC is in phase with IB. But now if I show, that is VDS is equal to VDD minus ID plus small id, that is I am showing it as a base, that is quiescent point, that is DC ID and the AC variation on it, okay, into RD. So this says that is ID RD, that is in negative. That means VDS is, when ID is increasing, VDS is reducing. That means overall, that is corresponding that this is the VGS reduction is this. Okay, so VGS is actually reducing in this phase. Okay, but overall you can see corresponding to this, VGS is also in phase, okay, with VIN. ID is in phase and VGS is also in phase with this thing. Okay, but VDS, because here there is VDS, sorry, here I have to show VDS. VDS is out of phase, okay, because when ID positive half cycle it is increasing, VDD minus that thing, that will be reducing. Okay, so that is 180-degree phase shifted. VDS output voltage, that is going to be 180-degree phase shifted with this, okay, with input V in. Okay, so this is similar to the BJT working, but only one more difference is because here there is a non-linear amplification, okay, compared to BJP having linear amplification. Fine. So there are few more type of configuration. This equation. If ID increases, suppose if ID increases, this is due to change in temperature. Suppose, okay. If ID increases, what happens? If ID increases, this drop increases, and that's why VDS reduces. Okay, VDS, that is reducing. That's fine. But as ID reduces, IDRS, that is reducing actually. IDRS reducing. When IDRS reduces, VGRS reduces, and that's why when the control voltage, gate control voltage is reduced, what happens to ID? ID will be again reduced. When the control voltage is reduced, ID voltage will be reduced. And when ID is reduced, that gets balanced. So in the next step, VG is reduced. So overall like this. Okay. Okay, I have not mentioned. But anyway, that is if ID increases, IDRS increases, that is VD increases. So that means VGS, that will be reduced, and that ID becomes reduced. So overall cycle is to balance the ID. So this is called why it is self-bias mechanism. And capacitor C1 and C2 are, as I said, they are for blocking, okay, and CS is actually a bypass capacitor we want to feedback the DC, but we do not want to feedback the AC, because if AC is feedback, your output is reduced. We want maximum AC output on the output side. So AC has not to be feedback. This will reduce the gain, because so we are not going to feedback the AC, and that's why a bypass capacitor is used. This is similar to BJT, right? Let us look at another type of biasing condition, that is when we have, let's say, fixed and self biases combined. That means we are providing the VGG battery as well as that is RS feedback resistance. So in this case, again VG, that is because VG, that is IG is equal to 0, so there is no drop across this is RG, this is 0. So VG is simply minus VGG. VG is simply minus VGG. VGS is equal to VG minus VS, that is minus VGG plus IDRS. This is minus VGG and plus, this is going to be plus and minus. Fine. Because ID direction is this. ID is going to be in this. It is N channel JFET. Fine. So ID is outgoing. Yeah. So again, for this network also, that is VGS is minus VGG plus IDRS, and VDS is equal to VDD minus ID into RD plus RS. Again, see ID, if we have to find, in that case the same equation, IDSS into 1 minus VGS over VP square. In case we have to design, it's an operating point condition, and from that from these two equations we can find out RS and RD. That means, say, this VGS voltage is not constant. VGS, that is biasing requirement for the, that is, say, if I show here this curve, okay, so this is the curve, and we have fixed, suppose, the IDSQ corresponding, that should be VGSQ. This VGSQ, that should be properly, that should be provided by the RS and R1 R2. Okay, but now with this combination, what happens is, actually ID, for a given ID, if you change the transistor, VGS may not be same, it may be somewhat less or more. In that case, there are chances that the Q point with the previous values of RS and R1R may get highly differed. Okay, so VDV is not a suitable configuration, not the most suitable configuration for JFET or DMOSFET. Right? Okay, so this is